Hi, I'm Ben-Yaakov. This presentation is entitled The ESL of Axial Electrolytic Capacitors with a Measurement Demonstration. I'd like to thank Itai for assisting in the lab measurements. And there is a disclaimer here that the commercial capacitors that are shown are for educational purposes only. There is no endorsement or recommendation implied. I'm showing here a number of capacitors. These are hybrid capacitors, hybrid electrolytic capacitor as a matter of fact. This is the SMD package. This is the soldering tabs or star connection with the tabs here. And here is the axial capacitor with two leads coming out, positive and negative, and usually the negative is connected to the body, which is conducting, and this is why you can get them with a sleeve for insulation. So I'm going to concentrate on these axial capacitors, and in particular to talk about the inductance, the ESL of these capacitors. The generic model of a capacitor is capacitance inductance. This is the internal inductance, ESL, and the ESR, which represent the losses. So if I look at the impedance of this capacitor as a function of frequency, and this will be a log-log scale, this is typically what we see. At low frequency, we see a behavior of a capacitance, 1 over omega c, goes linearly in the log-log scale. At high frequency, beyond the resonant point, we see a inductive behavior because the capacitor is like a short already. And at the resonant frequency, we actually see the impedance of the ESR because the impedances of the capacitance and the inductances are sort of canceling each other. So we see here the ESR, and this is now this value at the resonant frequency. Now the resonant frequency is of course a function of the capacitance and the inductance. Now, manufacturers are supposed to specify the inductances, but they don't do it sometimes. Here is TDK, which is very nicely specifying the inductance, the ESL of this family of capacitors. These are electrolytic hybrid capacitor. Here are the axial, and this is the soldering star type. And here we have this inductance, ESL, for different sizes because depending on the capacitance you have different sizes. So say for a length of 30 millimeter and a diameter of 16 millimeter, it's about 30 nanohenry. This will be for the axial capacitor. For the soldering star, it's between 6 and 8, say here it's 8, so there is quite a difference between these two. Now, Chemet does not specify the ESL at all, and but you can get it by contacting the company, which we did, and we've been told that the ESL of this capacitor, which is comparable in size, this is also a hybrid electrolytic capacitor, comparable in size and in capacitance to the one that I've just shown for the TDK, that the ESL for this capacitor is 12 nanohenry, and again these are the sizes of this capacitor. And if we compare the two, the two of them are hybrid electrolytic and about the same size. In fact, the Chemet is a bit larger or longer than the TDK, and the capacitances are about the same for the same capacitances, about 370 microfarad. We see that the TDK specifies it at 29, while the Chemet specifies it at 12 nanohenry, quite a bit of a difference. And we're going to probe into this question, why is there this difference? So how is the ESL measured? The most popular way to do this is by looking at the resonance. At the resonance, we know that the resonant frequency is 1 over 2 pi ESL C. If we know C, measure it, and then we sweep the frequency. Then at the resonant point, which is f sub 0, we can find what is, this will be the minimum impedance, and then the resonant frequency plugged into this equation that comes from here, we can find what is the ESL. Now the setup will include some means of measuring the voltage. There is a resistor for limiting the current at the resonant because the impedance is very low. And then there is a source, and usually you like to add a voltage bias to operate an electrolytic capacitor in a normal way rather than around zero. Okay, so it's a fairly simple setup that you can set in any lab, just as a matter of fact, and get the resonant frequency. And if you measure the capacitance, then you can get the ESL. So we have put together a setup like this. Here we are using an oscilloscope to look at the voltage and to look for the minimum. And then we have a signal generator, and then we have a limiting resistor, 180 ohms. And then there is a power supply for biasing, and the bias comes here in parallel. And we are looking at the voltage across the capacitor, looking for the minimum. In fact, we've taken more points. I'll talk about it a little bit yet later. So this is for the Chemet 370 microfarad, 16 millimeter diameter and 35 millimeter long, and this is specified at 12 nanohenry for the ESL. Again, the TDK, comparable size and type, it's about 30 nanohenry. So here we did this measurement and we got indeed 13 nanohenry, which is pretty close to what has been specified, and this is a reasonable difference that you'd expect from experimental measurements. And here I'm showing how good is the extraction of the parameter of this capacitor in terms of the capacitance, resistance, and inductance. And what we see here, and these are measurement points, and the curve itself is coming out of a simulation which uses this model with the parameters that we have extracted, and you can see that we have a very, very good model, and obviously this is the minimum point, and this is the frequency for which we can calculate, knowing the capacitance, we can calculate the inductance, which comes to be 30 nanohenry. But the question is this the proper way of measuring the ESL of axial capacitors? And here is my doubts. If you have a capacitor which is sitting on a PCB, and suppose you have two traces coming to it, the plus and the minus, eventually they'll have to split. There's no escape. And then you have here a loop, which means inductance, which is not part of the layout. I mean, it's not part of the PCB because there's nothing you can do to improve on it. This is part of the fact that this capacitor has two wires on the two sides, and you have somehow to get to them, and therefore you will have this loop here no matter what you do. There's nothing you can do about it. So you cannot say that this belongs to the PCB. This actually belongs to the capacitor. Same thing goes if you have actually a PCB with layers of plus and minus, and here I'm showing, say, this is the source of a, say, current, a ripple current. In the layers themselves, the lines might get together at high frequency. They are getting close one to the other, the current flow here. But eventually they'll have to split here and get to these points, and therefore you end up with this loop here no matter what you do. Now if you compare this axial capacitor to a soldering star type capacitor or package, you might say, then you see that here we are in a much better situation. There is a minimum loop here. So the ESL that is specified for the capacitor itself is pretty much what you have in the circuit. Not so here. If you just specify this part, then you are ignoring this part, which will be there no matter what you do, and therefore you cannot escape it. So when you measure the ESL, by looking at the voltage across the capacitor itself without taking into account any of the connection to it, well, you'll get the ESL of the capacitor, but this is not the value that you have to take into account when trying to see what is the impact of the ESL on the circuit. So in order to take this into account, we have changed the setup a little bit, and now it looks like that. We are measuring the voltage here, including this wire, which is, in this case, looks like a standing capacitor, but it'll be equally correct if you look it from here, because it's the same area, about the same area. So this represents the inductance both of the unit itself and also this extra line here that you're bound to have. This is where we measure. The excitation and the biasing is about the same, and for this we get 55 nanohenry. That's a big difference. This is almost now close to this value here, certainly not 12 nanohenry that is being quoted for this capacitor by Kemet. Now again, the matching is very good. These are the experimental points, and this line is based on the parameter of the circuit that we have estimated or extracted, and this again will be here the resonant point, and the result is that the inductance is 55 nanohenry. And then we did something else, and that is to switch the capacitor such that the minus will be here and the plus here. Earlier we had the plus here and the minus here. Now we have the minus here and the plus here. Now when we do this measurement, we get 45 nanohenry, less than we had before. We had before 55, so it's less than that. Again, the matching is very good, so I have no worry about the accuracy of this measurement. It's excellent, very, very good. So why is the difference? Well, the difference is because the minus is connected to the casing. So ideally, without having to worry about drops, potential drops or voltage difference on the casing itself, the potential here and here is the same, and therefore the contribution of this area to the inductance is very small because there's no current loop here. Okay, there is some, as I've said, because the way the current is actually penetrating the casing, but it's certainly not like having the plus here and the minus here. And this will explain the fact that we are now getting 45, a lower inductance than before. Still, it is higher than the inductance, the ESL of the inner structure of the capacitor itself. Now, if I look at this loop here without actually considering the capacitor itself, assuming a 40 millimeter length, this will be like taking into account some of the overhead here, and 10 millimeter wide. The capacitor itself is 16, so it's like 2 millimeters beyond the radius here. The inductance of this part here is already 54 nanohenry. Okay, so it has nothing to do actually with the capacitor itself. It's just the sheer wire going back and forth is already 50 nanohenry. So this is the main contribution of the inductance, as a matter of fact. So what are the conclusions here? Axial capacitor have inherently high ESL. Well, this is something that we would have guessed from the sheer fact that we have wires and some distances, etc. But the point is also that the ESL measurement by the resonant approach must take into account the lead loop, because this loop belongs to the capacitor. It does not belong to the PCB. And no matter what you do, you'll always have this additional inductance, and you have to take it into account. So this brings it to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.